Over the course of this video, we will learn about all of the new capabilities added to SeeSAR in this version 12.1, codenamed Narcissus, to enhance your computer-aided drug discovery experience. Those who wish to watch and learn about very specific topics from this tutorial can do so by checking the timeline annotations in the video description. Otherwise, sit back, relax, and let's together find out what's new in SeeSAR 12.1. As the video title suggests, in this walkthrough we will talk about two overarching topics. On the one hand, SeeSAR, which is until now predominantly been a structure-based drug design tool, makes its grand entry into the world of ligand-based design with the introduction of the Similarity Scanner mode, enabling users to perform fast 3D alignments or superpositions of small molecules on selected template molecules. On the other hand, in the realm of structure-based design, the existing fragment growing functionality in the Inspirator mode has been improved with a newer algorithm that is incredibly faster. Besides these core capabilities, SeeSAR also sees substantial improvements in usability with a newer look and feel to all tables across the application. Since these tables appear across multiple modes, let us start with looking at how to work with these new molecule tables first. The best way to start with this exercise is to simply load a set of molecules into SeeSAR. So now that we've opened SeeSAR and are in the protein mode, let's go over to the mode selector and switch to the analyzer mode. The analyzer mode is not only a place to pull in molecules from other modes, but also acts as a home for molecules to be imported into the application. The various functionalities built into this mode make it an ideal place for molecules to reside through entire projects. Now we're going to load a set of molecules via the usual SeeSAR menu on the top left corner of the application. Click on the fourth button from the top called Load Molecules and select the file from our computer containing molecules to load in. Alternatively, we could also drag and drop this file into SeeSAR or copy the file contents as text with Ctrl+C and paste it back into the analyzer mode with a keyboard shortcut Ctrl+V. Now I've loaded a .sdf file, but you could also load a file containing molecules in the SMILES format, that is a .smi file, or a .mol2 formatted file. Our molecules are now loaded into SeeSAR, and as we see here, the table is populated, and selecting or clicking on one of the table entries shows the corresponding molecule in 3D. The first thing we notice now is that we have an indication of the total number of molecules in the table shown right above the table header. And also we have a new serial number column to help us keep track of our position on the table. In our example, we have loaded 33 molecules from a file, and this is indicated by the number up here, as well as can be seen by scrolling down the serial number column. Hovering the mouse on a serial number column header tells us the order in which the table has been currently sorted. The tooltip text now reads, "Table sorted to show oldest entries first." And clicking on this button will now reverse the current sort order, which is also indicated by the change in the corresponding tooltip text, which now reads, "Table sorted to show newest entries first." So that is a quick way to change the sort order of your table entries and to also find out what the current ordering of your table is. Now, the next thing we will learn is not something entirely new in this version of SeeSAR, but it does lead us to learn something that's newly added in the current version. So we all know that almost all column headers can be clicked on to change the sort order of the table based on the selected column. So for example, we could sort this table by the molecule name column by clicking on the name column's header and the table is sorted by the molecule name, which in our particular case are all numbers, making it easier for us to understand the order. This type of action is of course possible on almost all columns. Now what happens as a consequence is that we end up changing the ordering of the table, namely ordering the table entries from its initial or original state. If we'd like to go back to the original state of the table, we come back to the header of the serial number column, which is now containing this curved arrowhead symbol indicating reset, and the tooltip text on it now reads reset table to initial sort order. And a click on this button does exactly what it says. We've now actually reset the table to its initial or original state. Our next learning goal would be to learn about what these individual columns stand for. And for that, we are simply going to hover our mouse over the column headers. The first column header reads checked, that we could click on these check boxes below to perform additional actions on those molecules that were checked. We will learn a little more detail about this in the later part of the video. The next column header with this push pin icon that reads 3D visibility is, as the name suggests, controls the 3D visibility of molecules that are checked with this button. For example, let's set the visibility for one of the molecules in the table, and let's go ahead and click on this push pin button. And now we notice that this molecule will stay permanently or persistently visible in 3D. Now let's make this exercise a bit more visual, shall we? For this, let's jump 2 columns and now get to the column that reads color molecule. No points for guessing what the functionality behind this column is. So let's click on this button resembling an artist or painter's color palette, which opens up this color palette dialog. And let's pick a color and assign that color to this molecule. Now clicking on other molecules on this table clearly shows that the visibility of the molecule with the push pin remains persistent in 3D. Alright, great. Now moving on, let's come to this star-shaped icon whose tooltip text reads favorite, that lets you know that you could mark certain molecules as favorites by simply clicking on this star icon. An advantage of being able to do this is that when you have an option to check only those molecules which are marked as favorites for additional post-processing. So let's mark a few random molecules as favorites, like so. And once that's done, let's click on the header of the checkbox column. And we notice that there is an option that says check all favorites. And now when we do that, we realize that only those molecules marked as favorites receive the checkbox. Next, we move to a very important column. And this is important because this column contains 2 interesting functionalities. Hovering the mouse over this column reads annotation, and as the name suggests, once again, clicking on the corresponding symbol opens up a digital sticky note. Now we could record short notes on molecules like so. Now we note that the name of the last editor and the date is also recorded on the note. If we now have annotations on a second molecule, we could do that on that particular molecule as well. And when now multiple molecules have annotations on them, this column can be sorted based on the timestamp registered on the annotation sticky notes. As you see, the molecule with the latest annotation is now shown first. We are not entirely done with this annotation panel yet. Clicking on this button below that reads Capture Scene will store the exact 3D position of the molecule, which can be restored at a later point of time. For example, let's say we want to save the 3D state of this molecule in this exact position. So we go ahead and click Capture Scene. And despite now changing the position of this molecule in 3D, clicking on the button that reads now Reset Scene restores our initial stored state back again. Nice. Next, we move on to another interesting column, which is again something that's new in SeeSAR 12. Mouse hovering on the column header on this fire symbol reads Active Status. What does that mean? This means that based on existing knowledge of the molecule's activity or bioactivity, we can assign the molecule to be active or inactive in SeeSAR. So let's say we know that the molecule has a certain experimentally determined binding affinity and is active against a particular target. We can now assign this molecule to be active by clicking on the fire symbol, which sets the molecule as active. Clicking on the fire symbol a second time changes the symbol from the fire to a snowflake, indicating that the molecule is inactive. In this way, molecules can be annotated as active or inactive and can be visibly identified in SeeSAR tables. This possibility comes in very handy while working with sets of actives and inactives, which is often the case in ligand-based drug design projects. We will in fact see this in practice later in this video. If we save a molecule in SeeSAR with an active status annotated to an SDF file, this annotation is additionally written to the SDF file as an SDF property. And the property field is called biosolvit.csar_active_status. Conversely, if we load an SDF file previously saved with these annotations on them, SeeSAR will automatically activate the respective status icons on the table. So let me for once clear the analyzer like so and load another set of molecules which already contain active-inactive assignments. Here we see this active status column is automatically populated now. So far, we've seen how we can use the table functionalities in SeeSAR mostly from the perspective of single molecules. However, in many instances, we would like to work with multiple checked molecules and assign persistent visibility, active-inactive statuses, or colors to them. To set persistent 3D visibility on multiple molecules within a range in the table, we first check a single molecule, hold the Shift key on our keyboard, and check the last molecule within the range, which activates the pushpin button and consequently persistent 3D visibility on all molecules within this range. The same action, done in reverse, can reset the assignment. This function is available on the permanent visibility, favorite, and active status columns. To assign a specific color to multiple molecules, we check the molecules of our choice like so, go over to the newly added circular button with 3 dots on the toolbar which reads Checked Molecule Assignments, go to the second option that says Change Color of Checked Molecules, and pick your favorite color. We also notice that any such assignment on multiple molecules can be easily reset by using the second option in this submenu. We also notice that the ability to set permanent visibility and set active or inactive statuses to molecules are also available via this Check Molecule Assignments button. We've now covered ground on all of the improved molecule table functionalities and are now ready to move on to learning more about the Similarity Scanner mode. As mentioned earlier in this video, the Similarity Scanner is SeeSAR's entry into the world of ligand-based drug design. As a heads up, Let's make it abundantly clear that there is a fully dedicated video on how the Similarity Scanner is to be used, linked in the video description. And with respect to this video, we will try to understand the basic goal that the Similarity Scanner tries to address and quickly learn how to use the mode effectively. One of the biggest questions that ligand-based drug discovery tries to answer is usually of the form: how similar is the 3D structure of a test compound B with respect to a known active compound A? Clearly, we are grounding this question on the well-known similarity property principle, which essentially states that compounds with similar structures should potentially also have similar properties. The Similarity Scanner answers this question by enabling fast and efficient 3D molecule superpositioning or alignments using the FlexS algorithm. The algorithm, whose publication is now shown on screen, determines the quality of alignments of a query molecule on a template molecule. The template molecule should be available in its bioactive conformation, and hence this molecule should either come in from a protein-bound state in a crystal structure or a high-quality 3D conformer generated either by molecular docking or by a conformation generation method. This is very critical to the process. The quality of alignments is determined by FlexX scores, whose values have been normalized to fall between 0 and 1 in SeeSAR. So SeeSAR transforms these FlexX scores to a star rating system to enable fast visual and easy qualitative analysis of these alignments. Star rating systems are commonplace and are easy to understand. In the Similarity Scanner, a 5-star rating means a perfect self-alignment or alignment between two molecules that are almost identical to each other, and lower star ratings indicate lower structural similarities between the molecules indicated by the underlying scores. Let's now quickly see how we can use the Similarity Scanner in SeeSAR. Now that we are in the Similarity Scanner mode, our first step would be to load a set of molecules into SeeSAR. We will now load a set of molecules which already contain assignments of actives and inactives on the file. And we also have a molecule that is previously determined to be a template. We've now got 10 molecules loaded, 5 of which are assigned active and 5 of which have been assigned inactive. We note that the molecule named template falls in the active category. Once we have the molecules loaded, a critical step to perform is to choose the template molecule, which will be kept rigid, and the molecule on which all other molecules in the dataset will be flexibly aligned on. Choosing the template molecule is simply done by clicking on this radio button on the molecule entry like so. Now, running the alignment calculation simply involves one click on this green play button. But before we do so, let's quickly check the different run parameters that are within our control. For that, let's open the Similarity Scanner parameters window over here. First, we see that we can change the number of poses that are generated per test molecule, which is set at 10 per default, a minimum similarity rating of 0.6, which qualitatively relates to 3 stars, means that any alignment that falls below 3 stars, which is essentially considered being poorer than 0.6, will be ignored from the results. Third, we see a new addition to all run parameters that involve some form of conformer generation, namely allowed ring conformation for 6-membered rings, which can be toggled to allow only the chair conformation by default, or the chair and twisted boat conformations, or all 3 chair, twisted boat and boat conformations together. We will leave this at its default setting of only chairs, which are the most energetically favorable conformations for 6-membered rings. Advanced users who would like to run large-scale calculations with the FlexS command line tool could export the FlexS definition file from here. Now that we've looked at the run parameters, let's go ahead and run an alignment calculation. We are now notified by SeeSAR that 3 out of 9 molecules could not be aligned. This is normal and could happen due to various reasons. The most common reason could be that we've probably set a very strict minimum similarity value. Let's reduce, in our case, the minimum similarity value all the way down to 0 and try to run a calculation again. There we go. It now seems like all of the molecules have been aligned, and now we can go ahead and take a look at the alignment results. To make the analysis easier, let's do a few things we've already learned. First, let us set the template molecule to be persistently visible in 3D, and let's give it also a color that it can be easily visually distinguished. Now let us sort our results based on the star-based similarity rating. We want to see the best aligned ligand molecules first and then the poorly aligned ligand molecules after. Now clicking through each row individually will help us visualize the alignment between the selected result molecule and the template molecule, which is permanently visible in 3D. We also notice that in this particular example, the actives align much better to the template compared to the inactives, which in this case easily supports the crux of the similarity property principle. Please note that this may not, however, always be the case with your experiments with the Similarity Scanner. That brings us to the end of the Similarity Scanner walkthrough, and we move on to the final topic of this video, namely ultra-fast fragment growing into cavities with FastGrow. Fragment growing is a very common method employed in the field of fragment-based drug design. In SeeSAR, the existing fragment growing algorithm has now been replaced with a new and improved FastGrow algorithm, which comes with a substantial boost in performance. A simple experiment conducted shows that the original fragment growing algorithm took close to half a minute to grow 100 fragments from a collection of just 100 fragments, while FastGrow takes just over 10 seconds to grow 100 fragments from a collection of 12,000 fragments. This is a clear demonstration of improvements in speed and efficiency of the FastGrow method. Now let's get hands-on with FastGrow. Let's open SeeSAR in the protein mode and load a simple protein ligand complex, namely the PDB ID 1STP. Once the protein is loaded, let's select the ligand BTN and let SeeSAR automatically define the binding site on this protein on the basis of this selected ligand. Next, let's right-click on the ligand in the molecule table and add this molecule to the inspirator mode. In the inspirator mode, let's switch the binding site surface visualization first to get a holistic view on how this molecule sits in its binding pocket. Meanwhile, we notice on the top section of the table that a larger fragment set is available for download from the Biosolve IT website. And if we are interested, we could go ahead and load a larger set. By default, SeeSAR ships with a collection of 12,000 fragments derived from the PDB to get us started working with FastGrow without additional downloads. To start running FastGrow, we first need to find a position on the molecule to initiate the growing process from. This is done either in 2D or in 3D by clicking on a bond on the molecule like so. Now, this means that the parts of the molecule that remain bright will be kept rigid and fragments would be grown into the grayed out or darker part of the molecule. The direction of growing can be changed by simply clicking on this pink disk one more time. A third click will remove the disk entirely and help us place the cut point at a different position in the molecule. Now with the point of growing defined, we simply need to click on this green button with a motif of 2 leaves, which is now shown as active. We notice that 10 fragments are grown almost instantaneously, and the additional calculation time is only to estimate the affinity and to calculate other properties. From the results, we also note that with this first attempt, we've not obtained molecules with better estimated affinities than what we started with. This is quite common, and it should only encourage us to try different points of growing and to try different settings and parameters. Basically run multiple iterations of FastGrow until you've generated a collection of ideas that can be further looked at. Clearly, the compute time involved in running FastGrow is no cause for concern, like we've already seen. Neither FastGrow nor any of the other computer-aided drug discovery methods are a one-stop solution to produce active molecules. So with FastGrow or any other available method here in the Inspirator, it is always recommended to take your generated molecules to the docking mode, redock them, and find if your proposals actually fit optimally into your binding pockets. That said, FastGrow is indeed a super fast and efficient method to help you arrive at active molecules, as validated recently by this published study. You could also read the study to learn more about the inner workings of the FastGrow algorithm and its implementation. That brings us to the end of this tutorial. As the closing words, I'd like to remind you that a complete list of updates to SeeSAR's newer version is available at our website biosolveit.de/SeeSAR/changelog. And also remind you of the fact that SeeSAR comes in with a context-dependent help system that is always available to guide you as you explore the application. We hope you had an enjoyable time and a good learning experience watching this video. We thank you for your time. Take care and goodbye.